chemistry, we're moving on to our second unit in this course. The longest one was the one you just finished on foundations. This is a unit that's very important. It's on chemical reactions and some of the fundamentals of working with chemical reactions and chemical equations. So the mole. A mole is that number. It's a very, very large number, and it can be of anything. But in this class, it will be of atoms, molecules, things of that nature. This number is called Avogadro's number, after the person who came up with this concept. In scientific notation, a mole, that number up above, is 6.022 times 10 to the 23rd. Remember, you can think of an atomic mass unit as the mass of either a single proton or a single neutron. Unfortunately, those masses are too small for us to weigh on any kind of a scale. So here's the problem. We can't measure the mass of a proton, neutron, atom, or molecule on a scale. So what do we do? An oxygen atom has a mass, and you get this off your periodic table, so be sure you know how to find this on your periodic table. It has a mass of 16 atomic mass units, but we can't measure 16 atomic mass units on any kind of scale. It's just too small. We measure the mass in grams, and we have scales for that. So grams is something that's the standard unit of mass that's used in science, and we have scales to measure that. So what if we knew how many oxygen atoms it would take to have a mass of 16 grams? In other words, the same number, 16, but instead of atomic mass units, it's in grams. There's some number of oxygen atoms that if you got that, just that number, it would be exactly 16 grams. So the only thing that would change is the unit of measure. Then by knowing the number of grams of oxygen we had, we would know how many oxygen atoms we have. That's really the significance. It's not knowing what the weight is. It's not knowing a certain number of atoms gives you a certain weight. It's that if you have a certain weight, you can then figure out how many atoms of oxygen you have. And that's what chemical equations work with. They work with numbers, not with weights or anything else, just numbers of particles. So there is a way that we can know how many oxygen atoms we have by knowing the weight of the oxygen that we have. So how many? What is that number that would get us from 16 AMU to the exact same number, 16, but measured in grams? So the answer, Avogadro's number, 6.022 times 10 to the 23rd, is the number of atoms that will convert the mass of a single oxygen atom, 16 AMU, to the same number of grams. So there goes the question mark, and there comes the number. So that number of oxygen atoms will get you to 16 grams. So the issue is they had to pick some big number, big enough for us to weigh and to be able to see with our eyes. And we can see 16 grams of oxygen. We can see a mole of oxygen atoms with our eyes. We can see a mole of water molecules with our eyes, and it's enough for us to weigh on a scale. So that's why it's important to have this big bundle, to have a big bundle of atoms or molecules. But the reason they picked this specific number, because it seems like kind of an odd number, 6.022 times 10 to the 23rd, because it gets us from 16 AMU for oxygen to exactly the same number, 16 grams. And it will do that same conversion for any element or compound measured in AMU. It will get you to that same number but in grams for any element that we deal with or any compound. So this is called the atomic mass, and this is called the molar mass. So get used to hearing that term. You're going to hear the term molar mass every day in this class. So this relationship is true for any element or compound by taking the atomic mass in AMU. Again, you get that off your periodic table, or by adding up elements to get a compound, and multiplying by Avogadro's number. So let's take carbon. The atomic mass for carbon, get this off your periodic table, is 12.01 AMU. When you multiply that by the mole, you get the molar mass, which is 12.01 grams, the same number, but in grams, something we can actually measure in the lab. Nitrogen, get this off your periodic table, it's 4.01 for a single nitrogen atom. But if you multiply by this many nitrogen atoms, you get that same number in grams, 14.01 grams. Neon, 20.18 on your periodic table, multiply by a mole, you get 20.18 grams. Aluminum, from your periodic table, 26.98 atomic mass units for one aluminum atom, multiply by that many aluminum atoms, and you get 20.98 grams. Sulfur, one more, 32.07 AMU, multiply it by a mole, and you get 32.07 grams. Okay, here's some common examples of chemical molecules and compounds. So H2. So what H2 means is you have two hydrogen atoms covalently bonded together, because it's a nonmetal. So two hydrogen atoms bonded to form one hydrogen molecule. So that is a molecule, covalently bonded. H2O, again, covalently bonded. These are nonmetals. One oxygen atom and two hydrogen atoms, so that does form a molecule. CO2 is one carbon atom and two oxygen atoms bonded together, and that forms a molecule. NaCl, now that's one sodium and one chlorine. That is an ionic bond. The sodium passed an electron over to the chlorine, as we saw back in the ionic bond lesson. So that doesn't produce a molecule. It produces a formula unit in an ionic bond, and you have a bunch of those that are in a crystal lattice structure, like apartments in an apartment building. O2, similar to H2, two oxygen atoms bonded to form one oxygen molecule. The small number of atoms is called, the small number after the atoms is called a subscript. A subscript of 1 is not written. So CO2 is really C1O2, but you don't have to write the 1. H2 and O2 are covalent bonds that form molecules. They are not compounds because they have only one element. A compound has to have more than one different type of element. If a number appears in front of a chemical formula, it means that there is more than one molecule or formula unit of that formula. So here's 2H2O. So that means you have two water molecules, two H2O molecules. So in all, you would have a total of 4 hydrogen atoms and 2 oxygen atoms total. So what does that mean you do? It means you take that coefficient, the number out in front, and you multiply that 2 by the 2 subscript of H, and that would give you 4 hydrogens. And you take that 2 and you also multiply it by the 1 subscript of O, and that will give you 2 oxygen atoms. 3 CO2 means you have 3 CO2 molecules. There are 3 carbon atoms and 6 oxygen atoms in those 3 CO2 molecules. 4O2 means 4 oxygen molecules. That means there's a total of 8 oxygen atoms in 4 oxygen molecules. The large number in front is called a coefficient. It indicates how many of the complete units that you have. The atomic mass of a molecule or unit cell is computed by adding the atomic masses of each of the atoms times the number of atoms. In moles, this is the same number, but measured in grams. So atomic mass of a single water molecule. So you have H2O, you have 2 hydrogens, each one is 1.01. You get that off the periodic table where the atomic mass is at the bottom of each entry. And then you have oxygen, which is 16. If you add that up, you get 18.02 atomic mass units for a single water molecule. So that's all from the periodic table. Now the molar mass of 1 mole of water molecules, that is 6.022 times 10 to the 23rd, you have exactly the same numbers you'll notice there. The difference is right there, grams. It's the unit of measure that changes. So the unit of measure changes from AMU to grams, which we can measure on our classroom scales. So let's try 2CH4. That's methane. It's also known as natural gas. So if we have 2 CH4 molecules, it means we have 2 carbons, and we have 2 times 4 or 8 hydrogens. So you simply add up all those numbers from the periodic table, and we now think of these numbers as molar mass. Okay, we're going to get away from thinking of them as individual molecules, masses, AMUs, and get to thinking of them as molar masses. So down at the bottom you see the mass of 2 CH4 molecules is 32.10 grams. Okay, now we're going to work a few examples, a few number examples. to get us used to working with atoms and moles. So we're going to do water. So we have hydrogen and oxygen, and they combine to form H2O, a water molecule. So how many atoms of hydrogen do we have? We have 2 atoms of hydrogen in H2O. How many atoms of oxygen? We have 1 atom of oxygen in H2O. And how many water molecules does that produce? That produces 1 water molecule. Don't make the mistake of adding 2 plus 1 to get 3. It's like if you're making a bicycle, you need 1 seat and 2 wheels to make 1 bicycle, not 3 bicycles. So that's what's going on here. You're putting the atoms together to form that molecule. Okay, so the atomic mass, we know how to do that now. We get, for hydrogen, it's 1.01 from the periodic table, and you have 2 of those, so that's 2.02. For oxygen, it's 16 from the periodic table. You have 1 of those, so that's 16 atomic mass units. And finally, now this is where you do add the numbers. You add the masses to get the water molecule. It's 2.02 plus 16 is 18.02 AMU. So now we're going to go over here and we're going to multiply everything by 6.022 times 10 to the 23rd, our magic number, the mole. So we're going to put a big red box and a little red box. I'll explain that in a second. So if you take 2 atoms of hydrogen and multiply it by a mole, you get 2 moles of hydrogen. If you take 1 atom of oxygen and multiply it by a mole, you get 1 mole of oxygen. And if you take 1 molecule of H2O and multiply it by 6.022 times 10 to the 23rd, you get 1 mole of water molecules. And then for the molar mass, we know that the number stays the same, but the unit changes to grams. So 2.02 AMU becomes 2.02 grams. 16 grams is the mass of a mole of oxygen atoms. And if you add those up, you get 18.02 grams, which is a mole of water molecules. So let's work a few problems here and see how this all comes together. So how many grams is 3 moles of H2O? So what you do is, everything in that box is referenced to 1 mole of H2O. That's the one that's in the little red box. So for 1 mole of H2O, you need 1 mole of oxygen atoms. For 1 mole of H2O, you need 2 moles of hydrogen atoms. For 1 mole of H2O, you need 2.02 grams of hydrogen. For 1 mole of H2O, you need 16 grams of oxygen. And for 1 mole of H2O, that will be a mass of 18.02 grams if you have 1 mole of water molecules. So how many grams is 3 moles? So there are 3 times 18.02 grams of H2O, which is 54.06 grams of H2O in 3 moles. So in other words, that 1 that's in the little red box, you change that to a 3. You don't want 1 mole, you want 3 moles. You multiply that by 3. So therefore, it's asking you for grams. So you would take the water, so that would be 18.02 times 3, and that will give you 54.06. How many moles of hydrogen are needed to make 4 moles of H2O? Well, to make 1 mole of H2O, in the little red box, you need 2 moles of hydrogen up there at the top in the moles column. So if you want 4 times that many water molecules, you need 4 moles. Then you need to multiply the 2 moles of hydrogen by 4. So there are 4 times 2 equals 8 moles of hydrogen are needed to make 4 moles of H2O. So whatever you have to multiply the number in the little red box, the moles of water, by, you multiply whatever other variable it's asking you for, or number that's asking you for there, by that same number. How many moles of oxygen are needed to make 3 moles of H2O? So to make 1 mole of H2O, you need 1 mole of oxygen. If you want to make 3 moles of H2O, 3 times as many, you need 3 times as many moles of oxygen. So there are 3 times 1, or 3 moles of oxygen, are needed to make 3 moles of H2O. How many grams of oxygen are needed to make 3 moles of H2O? So 1 mole of H2O in the little red box is, you're going to multiply that by 3. So that means you have to go up to where you see grams and a molar mass, grams and oxygen. So that's over there where you see the 16. So if you want 3 moles of water, you need 3 times 16 grams of oxygen, which is 48 grams of oxygen in 3 moles of H2O. How many grams of hydrogen are needed to make 7 moles of H2O? So to make 1 mole of H2O, you need 2.02 grams of hydrogen. So if you want 7 times that many moles of H2O, you need 7 times 2.02, which equals 14.14 grams of hydrogen, are needed to make 7 moles of H2O. Okay, so here are some ways of writing molar mass. So here is the molar mass for water, H2O, and we've already calculated that. It's 18.02 grams per mole, meaning if you have 6.022 times 10 to the 23rd water molecules, they are going to weigh exactly 18.02 grams. So there's several ways it can be written. One is called the equivalency. So it simply says 1 mole of H2O equals 18.02 grams of H2O. And I want you to get used to writing your units and your substance like this. You should always have a unit of measure, that would be moles or grams in this equation, and the substance that you're talking about. So moles H2O, that's unit of measure and the substance. Grams of H2O, that's unit of measure and the substance. So this is called an equivalency. It says 1 mole of H2O equals 18.02 grams. Now the way you'll often see it in a problem in a book or on a test is the molar mass of H2O equals 18.02 grams per mole. That's saying exactly what the equivalency is saying. It's just kind of a shorthand way to write it. 18.02 grams per mole is the molar mass of water. And finally, what are called the conversion factors. And all you simply do is you take the equivalency and you put one of those over the other. So in the first conversion factor you see, you take 18.02 grams H2O over 1 mole of H2O, or you can flip it. There's 1 mole of H2O for every 18.02 grams of H2O. Now, are those both true statements? Yes. Think about this. There's 12 inches in 1 foot. You could also say there's 1 foot in 12 inches. Okay, those are both true statements. You just said them in the reverse order. Same thing here. It doesn't matter. As long as they are equivalent, that 18.02 grams of H2O and 1 mole of H2O are the same thing, you can put them in either way. And you're going to see how to use conversion factors in the next lesson or two. Okay, so that takes care of our lesson on the mole. A mole is a large number of atoms or molecules, big enough that we can actually see with our eyes or weigh on a scale. And so we want to work in moles. We don't want to work and talk about individual atoms and molecules because we can't deal with them, we can't see them, we can't weigh them.